So after talking about electrical potentials and electrical potential energy and voltage, now is the time that we get into electrical current. I know you guys have come across that as well in your chargers and whatnot. And we often get worried about voltage, but what we should really be worried about is electrical current, because as you can see in this little video, it's not the voltage that's the problem, it's the current that runs through the body. Okay, so I don't think this is real. I think this is a fake video, but it often does happen. If you're not careful plugging in leads to a car battery, 12 volts doesn't seem like a lot of juice, but that battery can produce quite a large current through your body. So if this person's hand is touching one terminal and touching the other terminal by actually touching the metal, you can get zapped, and that can actually cause you to die. Okay, the amount of current that would flow through you would freeze all of your muscles, cause them all to contract, including your heart, and that's a problem. Okay, so you have to be very, very careful dealing with any size battery. The larger the battery, even a small voltage, if it can generate a large current running through you, it can cause problems. Okay, so the current is the big problem. Electrical current is the flow of electrical charge. More precisely, it is the rate of flow of electrical charge measured in coulombs per second. So rate is the big idea here. Okay, so current, the symbol for current in physics is I, all right? And current is measured in amperes, which you'd see as the letter A. All right, and what it is if you take the total charge flying past you per second, that's going to be amperes. So if 10 coulombs of charge flies through this guy's arms in 1 second, he's experienced a current of 10 amperes. And in all reality, I think a current of like 1 ampere or 2 amperes is more than enough to cause a lot of damage. Okay, so 10 amperes is way too much. Okay, so we have to be very careful. And in your homes, you have fuses, you have all these things that I know you've encountered, that you've had to change, okay, that protect us. They try to protect us from getting a lot of current in case you've actually plugged yourself into a circuit. So having circuits that don't have these protections for current can cause a lot of problems. So that's the big idea behind electrical current. In physics, current is the rate of flow of positive charge, even though that doesn't really happen in reality. As I showed you in the previous videos, the particles that move charge are not protons. Protons are stuck in the nucleus. Electrons move. But if you look in any physics textbook, they always show the movement of positive charge, even though it's fake. And that's because physicists knew about current a long time before electrons were even discovered. So because they're positive people, they always thought that electricity is a positive energy, okay? And so it's the movement of positive charge, even though positive charge doesn't move, okay? So that's an important distinction to make. So how does current relate to voltage? Okay, so we talked about batteries, and inside the last video, we talked about the electrical potential of battery. Okay, so negative, 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 positive, positive, positive. Okay, and these electrons over here would have high potential energy. Okay, and that potential energy is created by the electrical potential. 9 joules per coulomb times the charge of an electron would give me the potential energy. Okay, and then also what we did in the last video is show you how to calculate the kinetic energy of those electrons. So the greater the electrical potential, the greater the kinetic energy is going to be, the greater the velocity of that electron is going to be as it travels through the conductor. The greater the velocity, so if velocity is great, okay, then your rate of flow is great, okay? All right, so if my velocity is high, my rate of flow, okay, so rather than do that greater, then let's do something else. If my velocity is up, then the rate goes up, okay? Because that means that the speed of those electrons are going up. If the rate of flow is great, then my current becomes great, okay? Current is the rate of flow of charge. Therefore, my current is proportional to my voltage. If I increase the voltage, I will increase the current of charge flowing through my circuit. Now notice that I have connected this conductor, okay? So current is going to be flowing charge through a conductor, some type of metal. If I plug wood in there, wood holds the electrons, the atoms hold the electrons too much, and there'd be a high resistance to the flow of electrons. But if I put a conductor in there, electrons will flow very easily. And when I plug a battery into a conductor, what I'll be generating on either side of the conductor is a potential difference. Potential difference. Okay, and that potential difference across the conductor is going to be the same as the battery. It'll be 9 volts or 9 joules per coulomb. And that provides the driving force for moving the charge across the conductor. And like I said, the greater the voltage, the greater the current. Okay, that's the relationship. All right, so what would be the direction of flow? Well, even though we know that electrons are flowing in that direction, and that's really what's happening, and the chemists in the world all know that, the physicists still think that the direction of flow is positive. Well, even though they know it's not, but that's what our formal current is going to look like. So if they ever asked you, what is the direction of the formal current in this circuit, you would have to draw this one. You would say that the current is going from positive to negative, even though we know that electrons are flowing in the other direction. Okay, so current in a circuit, in this circuit, if I didn't attach that wire, no current would flow because I would not generate a potential difference across my conductor. Current only flows if positive and negative is applied to a material. Okay, and the rate of flow is not just limited to the voltage, because inside of that conductor, different materials hold those electrons and charges tighter than others. Okay, so current is limited by the flow of resistance in a conductor. So this conductor might resist the flow of charge. Okay, and some conductors like gold don't resist it much, but some other conductors like aluminum would resist the flow by a lot. Okay, so resistance is why conductors get hot. If there was no resistance, okay, then the electrons can flow through like a superhighway and everything would go really nice. But if resistance is there, okay, the atoms are holding on to those electrons. There'll be a bit of a tug of war when a potential difference is applied, okay, and that tug of war is going to cause movement. And movement is going to cause kinetic energy, and kinetic energy causes heat, okay? So if I have resistance in a conductor, it gets hot when I plug it into a battery. If I have a metal that has very low resistance, it doesn't get that hot at all, okay? So a good example of a metal that has low resistance is gold. So in really high level electronics, we use gold wires because they don't get as hot as copper wires and things like that. But low-grade electronics would use copper wires, and we have to be careful because they get very, very hot because the resistance in those wires is a little bit hot. Okay, so how does it happen? Well, collisions between charges and atoms cause them to vibrate and raise kinetic energy. And as we know, temperature is a measure of average kinetic energy from the last unit we did. The more collisions, the more resistance. The more resistance, the greater the amount of heat that's going to be created. So factors that affect collisions in a conductor and ultimately create resistance relate to these 4 things. The type of material. Okay, as I described, gold has very low resistance. Aluminum, the structure of the atoms and the way they hold the electrons, okay, gives that material high resistance. Okay, if I increase the cross-sectional area of the conductor, so if you go outside and you look at the power cables, those are really, really, really thick. And then you look at the wires inside of your iPhone, they're really, really thin. Okay, the greater the cross-sectional area, okay, so if I have a wire, this would be the cross-sectional, that's my radius, that's my cross-sectional area. Okay, so if I made a really fat cable, the greater the area, the more highways for those electrons to flow through that material. Okay, the more pathways it has to flow, there'll be less collisions between those charges as they're moving. So the greater the area, okay, the less resistance. The smaller the area, as I make that wire thinner, there's going to be collisions. There'll be more resistance, okay? The longer the conductor, the more chances I'm going to collide, okay? And if I increase the temperature, the atoms inside that wire are going to vibrate and probably make it likely to collide. So these 4 factors would affect resistance. Okay, so what does that mean? What does that mean? So if I go back to this conductor, if I raise the temperature, it's going to slow down the current. If I make that conductor longer, it's going to slow down the current. If I change the material, it's going to slow down the current. Okay, if I make the wire thinner, it's going to slow down the current. Okay, that's what we know just from experiments. Okay, and put that all together, a guy who experimented a lot with this stuff, his name was Ohm. Okay, and he created Ohm's law. And Ohm's law states that the current in a conductor is directly proportional to the voltage, as we described. When you increase the voltage, the current is going to go up. And it's inversely proportional to the resistance. The more resistance a material has, the smaller the current. you can rearrange that formula to come up with a more conventional form of Ohm's law, which is V equals IR. Almost everybody knows that formula, okay? So V equals IR. The applied voltage is equal to the current times the resistance, okay? And that's a very simple formula that we're going to learn how to use, okay? So let's put this together in some calculations. Okay, so here's a couple sample calculations. Calculate the current flowing through a conductor if it has 10 ohms of resistance and is connected to a circuit of 220 volts. Okay, so if I would go up to the wall, and here's my power outlet. If I go to the wall and I just take a wire and I plug it into one side and I leave it hanging there, there's not going to be any current flowing, so there's no current. Okay, why wouldn't there be any current? Because there's no potential difference. Okay, there's no potential difference on that wire. What I have to do is I have to connect the wire. There's two things I could do, which is very dangerous. If you took that wire, plugged it into one side, and you're still holding on to it and touching the floor, you would have a potential difference. Because if this is you, now this is very important that you don't do this, you are attached to the ground. Okay, and the ground always has a zero voltage, okay? The electrons can flow through you from high potential to low potential. Okay, so if you ever did that, you put a wire into one of the sockets, you would get electrocuted, because then what the socket would be able to see is a potential difference. So let's say this is 220 volts, okay, and then the ground has 0 volts, the potential difference would be 220 volts across your body. So never ever do that. But if you were somehow doing this and you weren't attached to the ground, you wouldn't have a problem. And then if you plug the wire into the other side, then you would have a problem because that other side is attached to the ground, and you would then have a potential difference of 220 volts. So a current would then flow. Okay, that's just an important thing to understand. I wanted to talk about that before we answer this problem. Okay, so how would I calculate the current? All right, so if there is a potential difference of 220 volts and there's 10 ohms of resistance in that wire, how would we calculate this? How would we calculate this? So V equals IR is one version. I can rearrange this. We're trying to calculate the current. So V divided by R is equal to I. So 220 volts divided by 10 ohms is going to be equal to 22 amperes. Okay, that's a lot of current. Okay, remember 1 or 2 amperes is more than enough to cause damage. 22 amperes would be a significant amount of damage. Okay, and that would explain why you never ever want to put a wire into the socket while you're touching the ground. That would be a disaster. Okay, calculate the resistance in a conductor if a current of 2 amperes flows through it when a potential difference of 12 volts is applied. Okay, so V equals IR, and we want to calculate the resistance. So I have to rearrange this formula to isolate from my resistance. V divided by I is equal to R. Okay, so then 12 volts divided by 2 amps is equal to R. So then 6 ohms is equal to R. Okay? That's what we got. Come on, you can do this. Very nice. Okay, so 6 ohms is equal to R. Now let's fix this symbol. I have a tendency not to draw that properly. Okay, so 6 ohms is equal to R. All right, that's that.